हेलो प्रवीण, और कोई आएगा कि बस दो ही लोग हैं ना?
Uh, Good afternoon, sir. Sir, I think I don't know whether they will be joining or not.
तो पर आई थिंक कितने पिछली बार दो प्रेजेंटेशन हुए थे ना?
Yes, sir. Last time we had two presentation and now I had to present and Ashish will be presenting.
ओके, आशीष को एक बार मैसेज भेज दो, देन वी कैन स्टार्ट एक्चुअली.
Okay, sir. I will send. I'm good.
Okay, I think we can start, right? Who is going to present?
Yes, sir.
Ravi?
everyone introduced, so I think I can start.
Okay, let me make you. Yeah, I have made you presenter.
My screen is visible.
Yes, visible.
Good afternoon, everyone. I'm Praveen Pandey. Today I'll be going to give a presentation on primes and P. This was the research paper written by Maninder Agrawal, Neeraj Kayal, and Nitin Saxena, and this paper was published in 2002. So let's look at the brief outline first. I will be going through the abstract, then I'll be introducing, then going through the SIVO virus first tenor, then we'll be going through FATS primality testing, then Mersenne prime series formula, primes in P, and then Fermat detail theorem, then AKS primality testing with an example of it, and then we'll be concluding it. So let's look at the abstract. So, and the overall abstract of the paper was an unconditional deterministic polynomial time algorithm that determines whether an input number is prime or composite, and that too in a very efficient way. So let's look at the introduction. So in complexity theory terminology, so is primes in P. The name primes is in P. The name of the paper. The first word primes signifies as a set of all prime numbers, and then the second P signifies as a class of efficiently solvable problems. There is the complexity theory part, P and NP part. Let's look at the brief history of primes first. So the first question that comes in mind, what are primes? So any number n that is greater than 1 and divisible by 1 and itself, it is said to be as a prime. Otherwise, it is composite. There are various examples we can look at: 2, 3, 5, 7, and other. And composite number as 6 is 2 into 3. So why do we want to know primes? So the primes are the atoms or the basic building blocks for all numbers. So there is a fundamental theorem of arithmetic that every number can be written as a product of prime numbers in a unique way. So as I already said, that primes are atoms or basic building blocks of all numbers. And to understand general properties of number, we need to understand prime numbers. Let's look at few observations. So there are 25 primes less than 100. So that means the 25% of all the numbers from 1 to 100 are primes. Of these, only 4 are less than 10. That is 40%. 15 are less than 50. That is 30%, and 21 are less than 75. That is 28%. That means the fraction is going to keep on decreasing as we move further. So there are few questions that comes to in our mind, and these are not only the questions, but these 4 questions are the overall mathematical advancement that has happened in the number theory. So for today, so how many primes exist? Can we estimate the number of primes less than some given number n? And the third question is, how do we find out if number n is prime? And then the fourth question, that how do we generate all primes less than some given number? So I will be sticking to these questions for my presentation. So let's look at the first. So okay. So so the first question, that primes have been of interest to mathematicians right from the beginning. So ancient Greeks used them in great details, and some of the earliest results came from them. So in Euclid's book of compilation of mathematical results during the Greek time, in his book the name of the book I remember is was Elements. So he proved two important results. The first was the fundamental theorem of arithmetic that we have seen in the previous slide, and the other he proved that there exists infinitely many number of primes. So our first question is answered: how many primes exist? So let's look at the second question. So for the second question, we have a sieve of Eratosthenes. So Eratosthenes gave a method to generate all prime numbers between 1 and n. So what this method basically does, we write down all numbers from 2 to n. take the first uncrossed number, say 3, and cross all multiples of 3 except 3 itself. So for example, I'm taking numbers from up to 30. So I'm taking the first number as 2, and I'm except 2, I'm crossing all multiples of 2, 4, 6, 8, and all till the 30. So the second figure shows the crossing of numbers. Now I take 3, and then except 3, I'm crossing all multiples of 3. So 6, 9, and up to the last. So similarly, I'm moving ahead. I'm crossing the except 5. I'm crossing multiples of 5, and then similarly, then we'll be going for 7, and the next uncrossed number is 7. Then we'll be going for 11. Then moving to the 13. Then for 17, we don't have anything because we cannot move out 30. So finally, we get the set of all prime numbers as 2, 3, 5, 7, 11, 13, 17, 19, 23, and 29. So our second question is answered. Our question number 4. The question number 4 was how do we generate all prime less than some given number n? So our question number 4 is answered by Steve of Tennis. So let's move further. So we can use the same method to answer question 3 as well, but that will be not very much efficient. So, but yes, we can use this method here also. So for this was done around 200 BC for the Greek time. But after 200 BC to 1600 BC, there was no advancement, mathematical advancement happened, and for the 1400 years, nothing happened almost. Then in 1601, in 1665, Comet came and he gave a beautiful expression of beautiful that for any prime number n and any number a raised to the power n mod of n equals to a. So we can look at various examples. We can raise 2 raised to the power 5 mod 5. We will get back to 3 raised to the power 5 mod 5. We will get back as 3. So this can be used as a property to test prime numbers. So given n, we choose some a and compute a raised to the power n mod n is equal to a and check if it is equals to a. So but this test was wrong. Because why it was wrong? So there were few numbers at that time identified. The smallest number was identified as 561, which can be written as a product of 3 into 11 into 17, and this number was found not to satisfy that test. And later on, we find that there are infinitely many chemical numbers existing. So this test was not. So moving to the machine prime. So for the machine prime, there was it was identified that 2 raised to the power m minus 1 numbers, where m is itself a prime number. So these are called machine prime. So for today, even the largest known machine prime was found out to be 2 raised to the power 134, 134, 669, 17 minus 1. But for the current, it is around 14 million digits, but that is also a machine prime. So there is a Euler's formula also that Euler gave in 1773. So this formula was basically that m square plus m plus 41. So the first 40 values of this formula are prime, and obviously 41 can't be the prime because it will divide the complete expression by itself. There is one more equation similar to it that was m square plus m plus 79. I can remember. So in this case also we will have up to first 78 numbers as prime, and 79 can't be the prime number because it will divide the whole expression. So around 1898, Legendre and Gauss came up with a conjecture that at that time this were not sure. They were not sure whether it is true, but they gave a conjecture that as n increases, number of prime number converges to we go n by log n, and this we also studied in our initial classes. So as a prime number theorem, and we studied it as a theorem because it was proved by Hammond and Belle-Poisson. So let's move further. So there are a few conjectures also that was there was a Goldbach conjecture that for every even number as two can be written as a sum of two prime numbers. For example, 16 can be written as 5 plus 11, 24 can be written as 11 plus 13, and there is a twin prime conjecture that prime numbers exist in pairs, that n comma n plus 2 both are primes. I mean they are twin primes exist. So and it was also proved that it was also identified that there are infinitely many number of twin primes. So we can have examples of 3, 5, 11, 13, 17, 19, and others. So there is also a problem factoring numbers efficiently. So no algorithm for this also. So as we have seen the twin primes, so there is also one more conjecture that how far can two numbers be. So that was also found out to be that was also given that n and n plus 3 times log of n and log of n cube. So but known today that it is the next prime is less than twice of n. That means if I have the number n, then next prime will be definitely somewhere less than equal to 2 into n. So let's now look at the 1973 Miller designed the test based that we have previously seen at Fermat's Peter's theorem. It was efficient as it required log of order of big of log of 4 of n steps, but it was assumed there was some form of assumption that was called as the Riemann hypothesis. So what was the Riemann hypothesis? So Riemann, there was a Riemann who was a student of Gauss. So he defined a function called Riemann zeta function. So it was thought that if we understand the zeta function, it is the key to understanding the distribution of primes. So the Riemann conjecture was that the zeros of zeta function lie on a straight line in a complex plane. So but since it was a conjecture and it was based on that Riemann hypothesis, so that is also we cannot rely on it. So after that, there was a Miller algorithm to obtain unconditional and randomized polynomial time algorithm. So, but again, this was based on probability. That is, that was for some tossing a coin. It was based on some probability that if you toss a coin and then based on the outcome, it was predicting. So basically, it was failing for the composite numbers and for the prime numbers, it was working very fine. So this was it. Let's move to the next. So this was to the solo-based systems. Okay. So in 1983, Edelman and Pomerance and Rumley gave a deterministic algorithm running in log of n raised to the power p into log n. So somebody remarked that log n goes up to infinity, but it empirically found to be less than equal to 4. So for this algorithm, Edelman and Pomerance gave a deterministic algorithm. And for the next, then Edelman, there was Goldman and Killian. They also gave a randomized algorithm, and then Edelman and Hogg improved it. So in 2002, AKS came and he gave the deterministic and unconditional AKS, Agarwal and Kalyan, and the main research paper is this, which is based on. So in 2002, AKS gave a deterministic and unconditional polynomial time algorithm for primality testing. So what was the algorithm? So the algorithm was we have an input n. So what we output as a composite if n is equal to m raised to the power k. So if for k greater than 1. So what we are doing is that we are finding the order of n. So what is order of n? So ORDN or ORN. It is the smallest k with n raised to the power k is equal to 1 mod r. So we are finding that value of r, and if any number less than r divides n, we output it as directly as prime or composite. And then for the step 4, we are moving for every a less than equal to 2 into under root r log n. What we are doing, x plus a raised to the power n. If not equal to x raised to the power n plus a mod n, comma x raised to the power r minus 1, then we output it as composite. And we'll be looking at to this as an example also. So let's look further. So what are the features of AKS primality testing? The features of AKS primality testing are the AKS algorithm can be used to verify the primality of any given number. The maximum running time it has came at that time was the order of log 21 by 2 n. So the algorithm is guaranteed to distinguish deterministically whether the target number is prime or composite, and correctness of AKS is not conditional on any subsidiary unproven hypothesis. For example, we have seen that there was a algorithm based on Riemann hypothesis. So there's no sort of dependence also here. So let's look at it as an example. So as a should be prime to n. So for the x plus a raised to the power n, this a is that one. So what we are taking at, we are choosing a value as 1, and then x minus 1 raised to the power n minus x raised to the power n minus 1. It must be divisible by n. So for suppose we take n as a 3 value, then we put that n 3, and then we expand the complete equation. So what we see that all the terms will get cancelled out which are not whose coefficients are not multiple of 3. So since 3 was a prime number, so finally we obtained the equation as of which the coefficients are multiple of 3, or we can say that divisible by n. So we can say that n is a prime number in this case. So there's an example also for n is equal to 31 based on the algorithm. So this for the 31 part we first input n, then output we composite if n is equal to m raised to the power k. So this part is done in the first step, and then we are finding that finding the smallest number r such that order of r is equal to 4 log n square. So we are doing this in the second part. So we found out r as 29 in here for n is equal to 31. So what we did in the third step, if any number less than r divides 10, then we output as a prime or composite appropriately. So this we are doing in the third part. We are finding the GCD of all the numbers from less than 29, because we found out as r to be 29. So we are computing the GCD of 29, 31, and 28, 31 up to the last. For example, for the last is here will be 2. So after we are done with the computation, now what we will be going through for every a less than 2 root r log of n, if x plus a raised to the power n is not equal to x raised to the power n plus a mod n x raised to the power r minus 1. So what we can do, we can compute the difference of both of these terms. So if we are getting every time as 0, then we can finally go ahead and conclude that we are having the prime number. So this is in the step 5. So we are for a is equal to 1 up to phi of and this phi of r is nothing but the Euler-Torsion function. So of log of n. So we are doing this computation that we are computing x plus a raised to the power n is not equal to x raised to the power n plus a mod x raised to the power n minus 1 comma n. So for that part we have calculated x plus a raised to the power 31, and then x plus a raised to the power 31 comma x raised to the power 29. The r we find in the step 2. And then what we are computing, we are computing the difference. So here 1 raised to the power 31 minus 1 is 0. So every time it must come 0. So since we have obtained as equal, so we can output it as output prime. That is 31 must be a prime number. So this is the code, but this is not the actual implementation of that. We have done the implementation using the Pascal's triangle for the small part. So here this is the coefficient matrix. This is more or less based on the first example that we have seen. This one. So this concept we have used here was for the smaller number of inputs. So we are computing the coefficient of that equation that and then we are checking here is prime in this condition I minus 1 and c of I modulus of 2 modulus n is equals to 0. So if we are obtaining all numbers as a divisible by n, then we output it as a prime. Otherwise, we output as a not prime. So if we look at the asymptotic complexity of this algorithm, so the asymptotic complexity of the algorithm was found out to be we go of log of 21 by 2 of n. So the main part, the complexity part, is that in this algorithm is the step 4, because if we in this step, if for the large number of large values of n, this is the step 4 will only matter, and for this from this the main our complexity part that comes out to be as a we go of log of 21 by 2 n, that is 10.5. So the further we can also improve this complexity to we go of log of cube of n if this conjecture is good, and the conjecture is that if r is a prime number that does not divide and if x minus 1 raised to the power n equals to x to the power n minus 1 mod x raised to the power r minus 1 comma n, then either n is prime or n square is equal to 1. So let's look. I think it is covered. So let's have more look on the asymptotic complexity part of the algorithm. So since we are having some time, so we can the first step input, we are taking input n, and then the first step we output composite if n is equal to n raised to the power k for k greater than 1. So this first step takes we go of log of cube of n. So for the second step, we find R with the order of n greater than log square n. So this can be done by trying out successive values of R and testing, and this is power k is not equal to 1 mod R. So for every k less than log square n, we find for uh, we can see that for a particular R we go of log square n multiplication. So total time comes out to be R times of log square n. So also we know that from the paper that we go of log raised to the power 5 and different R's needed to be tried, and this was based on a lemma given in the paper. So for the next step, we involve calculation of GCD of R numbers. So each computation takes the GCD computation takes order we go of log of n. So we are doing that for R times. So we will have that as or we go of R times log of n. So which came out to be we go of log raised to the power 6 n. So for the main part, that the step four I was saying that the majority part will be based here. So here, what happens that this equation that we are computing as if x plus a raised to the power n is not equal to x raised to the power n plus a. So each equation requires order big O log of n multiplication for degree r polynomial with coefficient size of big O of log of n. So verification of each equation can be done in big O of r into log square n steps. So the time complexity we can say that we are doing it for as our a value is ranging from 1 to less than equal to 2 times of under root r this r log of n. So we can come out to this as we go of r times of under root of r into log square n into log of n. So which we can further reduce it as a we go of r raised to the power 3 by 2 log of cube of n. And now what we can do further here is that so we can say that log of r raised to the power r we know that r is the order of r is in the order of log of raised to the power 5 into n, which we have seen in the step 2 that I said. So we can replace that r with that value, and we will finally getting the log of raised to the power 21 by 2 n. So this was for the time complexity part.
So actually, for this step 4, do you have looked at the proof that x plus a raised power n is congruent to x raised power n plus a? That stuff. Uh, when it is prime, that characterization, that lemma actually. Do you look at the proof of it or?
For that proof part, yes, sir, I have gone through, but I have not included that part in here.
Okay, but that's the important thing actually. How, because that was the lemma that was discovered by Somnath Viswas and and Maninder Agrawal, right? His guide, and that was a crucial thing actually. Anyway,
So that was lemma 4. I am remembering. I'm not remembering the exact number that was, but
okay. Thanks. So actually, total. So there are. So I think Ajit has presented, Komal has presented, and Praveen has presented. Then Ashish is left. The one more person is there, right?
No, sir, there are only 4 of us.
4 of us. Okay. So
can I
just
stop?
there was some other person, Jayaprakash Lal Chandani. Who was that?
Sir, that was me. I mistakenly logged in through my TSR's account.
Okay. I thought, okay, I thought, I don't know who is this guy, maybe another new person. Anyway. Okay, so now you can actually, who Ashish is left, right?
Yes, sir.
Yeah, so you can start, yeah.
Thank you, sir.
Sir, can you permit me to share my screen?
Yeah, I'm doing that.
Yes, sir.
Yes, you can start now.
Yes, sir. Yes, sir. Just a minute, sir. I hope my screen is visible.
Yes, visible. Good.
Okay, sir.
So you got some idea of qubits or something like that? You read it from that book?
Yes, yes, sir. I read the very introductory part of qubits, and then I also watched the some MIT lectures in which quantum mechanics was being discussed.
Okay.
So I kind of got a gist of what superposition is, and there were some experimentations that were being explained in that lecture. So I got a little bit of idea how these qubits are, the new nature of qubit is.
Okay. Okay.
More than that, I didn't go deep enough into the quantum mechanics realm.
Okay. Okay. No problem. Yeah.
Yes, sir. Okay, so good afternoon, everybody. The topic for my discussion here would be Shor's algorithm, and we'll be briefly touching the realm of quantum mechanics and quantum computation, just to know how quantum computation is actually making quantum computers are actually going to be the next state of the art means of computing things. So my presentation would be briefly introducing you the problem of integer factorization. Then we'll talk about the classical computers being slow for doing some problems. And then we'll talk about how quantum computation would be doing that. Quantum computers would be doing that very fast than the classical computers. Then we'll briefly touch about cryptography and how the prime numbers are being used in cryptography. And after that, I'll introduce to you the Shor's algorithm in the quantum realm, and then I'll wrap up my presentation. Okay, so beginning with integer factorization, what it is. So integer factorization is the decomposition of a composite number into a product of smaller integers. And if these factors are further restricted to prime numbers, the process is called prime factorization. And this is a difficult problem to solve. So this could be seen as an example of prime factorization of base 16. So these are some state-of-the-art algorithms.
Ashish,
These are some. Yes, sir.
hello, Ashish. Sorry to interrupt you, sir. Could you please mute
Yeah,
your mic because we are not able to hear Ashish's voice.
Can you see now? I think there was some problem.
Yes,
so
sir.
your
Ashish, could you please continue?
Okay. Okay.
yeah, so your mic was on. So yeah, so these are some current state-of-the-art algorithms that are being used for integer factorization. And these are some special purpose algorithms, and for general purpose, there are some more algorithms. But the topic for our discussion would be Shor's algorithm for integer factorization. So brief touching about the limitations of classical computers. There are a lot of things that classical computers have made us do efficiently, like integration of them in electrical devices, making our lives easier. Just for some examples, you can consider our phones and our laptops, the internet that we are using, the talks that we are doing to farther distances just through uh, these devices. But considering all these efficient stuff and all these help that these computers are providing us, still there are some things that these computers, the classical computers, are unable to do efficiently. And integer factorization is one of those problems. For example, if you consider the medical implementations of these simulations of chemical enzymes, you can see that we're only able to, sorry, we're only able to simulate some very small molecular structures through which we are not able to get the complete information about what the complex enzyme could be. So right now we are only able to So just giving the gist of the scalability of the problem right now, that we are only able to simulate molecules with eight atoms in it. So uh, just an just a representation of how scalable, how on a low scale we are able to compute and simulate the chemical enzyme right now. So what's the problem here? The problem is that as the scale of these problems rise, it is the difficulty to solve these problems grow exponentially. So we're bringing in quantum computers now. So what quantum computers are? They operate on the principle of quantum superposition and interference. And this quantum superposition is actually the fundamental principle of quantum mechanics. And it states that the states of the qubits can be superimposed. So what is a qubit? So bits and hello qubits. So qubit is a quantum logical state that the quantum computers operate on. And it is represented in direct notation that you can see on the screen. So in binary bits,
How to read them? Cat 0 and cat 1.
yes, sir. You can use the cat notation. So the pipe here is called, the pipe is called cat and the angular bracket is called a bracket. So using that notation, we call it a bracket, and this is in direct notation. Okay, so the binary bits are definite, discrete zeros and ones. But what's different in qubit is that qubit could be anything between 0 and 1. So it is actually a spectrum of all the variables that could be from this limit. Okay, so integer factorization and cryptography. So cryptography deals with rewriting of information in a format which is meant to be understood by the intended person only. So integers, more importantly, integers which are a product of large prime numbers are what are keeping the cryptography working at the moment. So we use large numbers to encrypt our messages, and then the factor of that large number is generally two prime numbers, in which one is used as a private key for the encryption party, and the other prime number is used as the decryption key for the second party. Okay, so factorization. So factoring a big number is a difficult task, and it takes sufficient. And if we take a sufficiently big integer n and factor it into its prime decomposition, factor 1, 2, factor n, it is very hard. So if you take an example and consider a number 39,843, and if you want to break it down into factors, it would be very slow for classical problems. So we can to get a gist of that, we can compare this problem from RSS 768. So if you want to factor that 768 number, so it will take a classical computer almost approximately 2000 years to solve. So what we can conclude is that classical computers are able to solve a problem of integer factorization, but they're taking a lot of time. But quantum computers are guaranteeing the solution, and they would be doing that in ridiculous fast manner. Okay, so we're coming to the main star of the show. So Shor's algorithm. Shor's algorithm was proposed by Peter Shaw, and it is meant to be a means of faster integer factorization on a quantum computer. And it takes the advantage of quantum superposition principle and interference. So Shor's algorithm is a polynomial time quantum computer algorithm for integer factorization. And informally, it solves a problem given an integer n. It finds its prime factors. So what if there is a number and we don't have its factor? So if that happens, then finding the number, the prime factors of that large number, uh, using which the encrypted data was the message was encrypted, couldn't be decrypted unless the prime numbers are known to the adversary. So right now, if he'll be using a classical computer, it will take him a lot of computation power, also a lot of time. So what he'll be doing actually would be he'll be guessing a factor, and then manually check it whether it is a factor of that large n or not, and he will repeat this process till eternity, till he'll gradually find the prime number, which is highly unlikely. Even if he uses some smart approaches to find factorization, it will still be slow. So this inability to compute the factors isn't actually securing the information till eternity, but but till the time the primes are computed, which is right now really high. Okay, so what Shor's algorithm is doing? Shor's algorithm is basically taking an integer, which will be a guess factor by us, as the supposed factor of the number n, and then try factorization for that large number n. And if it fails, it will take a better guess and then try again until the actual factors are found. So what do we mean by a better guess? So it is proposed that if I take a guessed number and raise it to power p, uh, uh, if I add or subtract a number integer 1 from it, it will be giving us a better guess than the previous one. So I'll talk about this in the incoming slides. For now, let's just consider this example. So we have this n as 15. So let me take g, our guessed integer factor, as 2. So 15 is not divisible by 2, so it will fail. And now I'll use this formula to create a guess which will be better than the previous one that I had. So if I raise my 2 to a power of 2 and divide it by 2, adding 1, I get 3, which is a better guess as it will be dividing my number. So I get the factors 3 and 5. So guesses can be actually of two types. It could be a direct guess. So what do I mean by direct guess is that the guess that I've made will actually be the direct factor of that number. So my number would be equal to my guess multiplied by another factor that would be uh, multiplying and giving me the number back. Or the guess could be a shared guess. So what do I mean by shared guess now? Shared guess would be, for example, I have a number and there are two factors of it. But what I guessed was a factor of one of those numbers, right? Okay. So sharing, the shared guess, is it okay to use? Yes, apparently it is okay to use a shared guess as it has been proved by Euclid's algorithm that uh, so in case you find the shared factor, the other factor could be simply computed by dividing n by the shared factor. So we'll get two numbers. One would be a shared factor 1 and the other one would be the number divided by the shared factor. Okay, so now we found out all the factors, so problem is solved, right? No. So finding a factor at the very first guess is highly unlikely. So it's probably not going to happen that your first guess would be the factor for the larger number n. So instead, you'll have to transform our naive guess into a more intelligent guess. So that was being given by guess to the power p by 2 plus minus 1. So we'll discuss that. So this is based on a very simple mathematical fact that two whole numbers that do not share a common factor, right? Suppose a and b. So if we multiply a sufficient times, so it will come back to, so it will result in some integer m into b plus 1. So that could be consolidated as this equation a to the power p, where p is the number of times that I'm multiplying a to get m multiplied by b plus 1. So let's consider this example. So we're considering two numbers with no common factors, 7 and 15. So I'm taking 7 and I'm raising it to powers to check whether at some power p and some integer m, it's coming to be equal. So you can see that 7 raised to the power 4 is actually giving me GCD1. So, okay, now what? So this isn't actually what we discussed earlier. So we had this equation, g to the power p by 2 plus minus 1 for the better guess. So let's transform this, this new equation that we got. So I'll subtract 1 from both sides, and then I'll break the left hand side down into the property a square minus b square, which will be a plus b into a minus b, and hence, yeah, so if I consider left hand side, I can write it as a g to the power p by 2 plus minus 1. Okay, so now we're one step closer now. So if we consider the left hand side, we can see that our integer n is now written as a product of two numbers. So the first number would be g to the power p by 2 plus 1, and the other one is g to the power p by 2 minus 1. So since on the right hand side we have multiplied n by m, the right hand side must contain shared factors of n, right? So you can see here in the last equation, m is being multiplied by n, right? So this might give us an idea that the left hand side, actually the two terms on the left hand side, could be a factor, a supposed factor multiplied by some another integer. So what do we now do now? So if we consider our previous example, so 7 to the power 4 was actually giving me that result. So if I apply that here, so I'll get 7 to the power 4 by 2, which will be 2 plus and minus 1, and I'll get 50 and 48 as two integers. So we see that neither of which are equal to 15. But if we consider in more depth, we actually can see that they are shared factors which can result into 15, which can be computed using the Euclid's algorithm. So we know that 50 can be written as 5 into 10, and here 5 would be our shared factor, and 48 can be written as 3 into 16. Here 3 would be a shared factor. Okay, so now we have the factors. Now we can break the encryption. So that's it, I guess. No. So there are a few problems that are existing in regards of the shared guess. So one of the shared guess, there are some problems. So these are the problems. One of the shared guess might itself be a multiple of n, right? And the other guess would be a multiple of m. So neither of these information is useful to us. Actually, they will be increasing the confusion. And the p might be an odd number, causing the p by 2 power result as a fraction, which will most probably result in a non-whole number. But the numbers that we are using to encrypt messages are whole numbers. And the third and the most important problem is, how do we find the p? Okay, so the first two problems that we discussed, they are not really relevant right now, as on experimentations, we have observed that 37.5 times the guess factor would work and it will break the encryption. So this means that if we're making 10 tries, at least 10 tries, there would be a certainty of 99% that you'll find the factor and you'll break the encryption. So now we're finding P now. Okay. So we discussed that we need to multiply the guess factor G a certain number of times to satisfy the equation G to the power P by 2 plus minus 1, where G is our guess factor and P is the number of times that we are supposed to multiply our guess factor. So our classical computers can find P for small n's like n equals 15, n equals 21 and 25. But for larger n's with 1,000 digits, even if our guess factor has 500 digits in it, it will take a lot of time for brute force factoring for finding this p value by using a classical computation, and even it will be taking more time than the brute force. Okay, so coming to quantum mechanics and how it will be helpful for us to do this. So unlike classical computers, which would result into one answer, a quantum computational computer would result into a spectrum of results simultaneously for a single input using the principle of quantum superposition. So, but we'll get only one result in the end with the probability, which is different from the spectrum of the results produced. And also the spectrum of results that I'm talking about would be produced in such a way and arranged in such a way that all the irrelevant elements of the result set would destructively interfere within each other and cancel out each other. And the answer that we'll get would be the correct answer that we require. So how are these quantum computers faster? So for a quantum computer, the function is set up in such a way that the input is a set of quantum superpositions that compute all the answer at once, and the final result is so produced that when the result set elements are arranged in a certain fashion, they destructively interfere to most likely produce the correct answer. So we feed the input, but we have to decorate the inputs in such a way that the quantum function could be able to take that input. And Shor's algorithm is actually doing that for our RP. So let's rewind and consider what all we have discussed. So we know that we need a guess factor G, and we need to find the power P such that G to the power P equals m into n plus 1, and P should be such that G to the power P by 2 plus minus 1 share factor within. Okay, so setting up the quantum machine. So we are feeding a number x as an input, and our guess factor G is raised to the power of x. Then this result is checked how greater of a multiple of n that is, and the remainder is saved as r. So here you can see we are taking x as a superposition, feeding it to the quantum function, and it will be taking x and it will raise g, our guessed factor, to its power, and then it will check whether, and it will store the resultants after dividing that. So since it is a quantum machine, the inputs can be sent as superposition of numbers and computations can be performed simultaneously. So instead of giving one number x, we can also give a superposition of different numbers, and it will do the same thing, raise it to the power of, guess to the power of the number input, and it will produce a result set which will be also a superposition of numbers. Then it will check whether the result that we have got is actually greater than m into n, and then it will produce another superposition according to that. So how to get the correct output? So this will result in a random output from, we'll get a random output from the resultant set, which would be anything. So this would be as equal as doing this on a classical machine with a random guess. So this is of no use for us. So we'll have to organize a result set cleverly such that the result set elements which are not required are cancelled out from our result set. So what is the strategy that we're going to take to set up our result set to get P? So P would be the power. So we have to cancel out all the non-P elements from our result set. So to do that, we are left with the answer, which will give us P. And this can be done by observing the simple mathematical equation that G to the power x equals m into n plus r. But also if we add something to the power x, it will result into same, but the number that we are that would be the multiple of n would be different. So basically this is also the crux and the core of the Shor's algorithm. So you can see this here. This is a basic demonstration where g raised to the power p is equal to m into n plus 1. But if we take g to a power 42, it will be some other number than m multiplied by n plus 3. And if we add again p to that number, some another factor m2 would be there, but you can see that the remainder would remain same for the case of 2p also. So we can also see this kind of a proof how this is working. So I'm taking g to the power 42 plus p, breaking it down into g power p multiplied by g power 42, breaking it down into further simpler calculations, and in the end we can see that the term m into m1 into n plus n3 into m plus m1 is the term that is different. Other than that, 3 remains constant. And this will work for all the powers of G. So what we can deduce here? So we can deduce that the P that we're looking for to make our guess factor intelligent actually has this repeating property. So we can see that G power X and G power X plus P, G power X minus P, and G power X plus 2P are giving us a period T. And whichever the term may be, the plus R remains the same. So let's take the advantage of this observation. So we can feed the input to as a superposition, and all the computations would happen simultaneously to produce the result set as discussed before. And we can actually use this property of P to destructively interfere the non-required elements from the result set and finally get a correct answer. So if we take the superposition of all the possible powers and compute the value of R, then we'll randomly get a possible value as output. This means that we're not left with the result elements, which are purely the power of that randomly selected number that would have resulted in the remainder of that number. So this is a very special property of quantum computation. So to demonstrate that, there is an example. So if we consider the following superposition in which I'm feeding these values as a superposition to the function. So if we randomly select the remainder plus 3, which is the middle term in this demonstration equation, then we are left with the superposition of terms which are only having the remainder as plus 3. So we can see that only these terms are left now. So these parts are all P apart from each other. What I mean by this is actually P would be a period for the superposition now. And if this superposition is repeating over the period P, so I can find the frequency here, which would be 1 upon P. And if I find this P, we can finally break the encryption. So to find the P, I'll inverse this frequency and I'll get P. So this is basically the idea of how it's going to be in the further slides. So introducing Fourier transform. So best known method to find the frequency of things is the Fourier transform. So what Fourier transform does is that it takes an audio signal as a waveform, then it produces a graph showing different frequencies of the audio that it is made up of. There is also a quantum version of the Fourier transform, which we will use to find the frequency of our Fourier quantum superposition. So if it input some superposition to our quantum Fourier transform, it will give us the frequency. So how does quantum Fourier transform is helping us? So if we input a single number to the quantum Fourier transform, it produces a superposition of all the other numbers which are weighted by different amounts. So, and those weights are roughly making up a sine wave with the frequency of the single number that we have fed. So if we take another higher number than the previous number, the sine wave which will be produced by the weights of the superposition that are made by the quantum Fourier transform would be actually more than the previous frequency of the previous number, smaller number. Okay, so if we feed a superposition of number to the QFT, then it produces a superposition of superpositions. So in here, if we're providing the superposition of numbers, the resultant set would be also a superposition of the superpositions that were produced by the QFT, and it will result as a destructive interference of both the superpositions that are produced. So why does that happen? So this happens because when a superposition with the same period P is fed to the QFT, all the sine waves that are produced interfere, and then we get a single quantum state representing 1 by P, which will be the frequency. And all the rest waves destructively interfere and cancel out. So if after that we get 1 by P, which is our frequency, which we can invert to get P and check if it is even. If it is, then we'll make an intelligent guess by using the formula G to the power P by 2 plus minus 1. And if it is not a multiple of n, then that means that it shares factors within. And now we can use our Euclid's algorithm to find the other factors. So that's easy. So what Shor's algorithm is that we'll get a guess of random factor, feed that random factor, and get P from the QFT using Shor's algorithm. then make a better guess and repeat the process until we get the factors. So our conclusion would be that we can take the encrypted data and decrypt it, and this is how actually Shor's algorithm work. So, and for a classical computer, checking for every number till n, starting from 2 would take a long time, as n could be as high as any number and p could be as high as any number. Guessing p would actually increase the computational load on the classical computer. But the quantum version is ridiculously fast. And in case of a sufficiently large quantum computer, if it is synthesized, Shor's algorithm can actually bring the whole internet down by making decryption really, really accessible to everybody. So on ending notes, right now the quantum power that can be generated can only factor small numbers like 15 or 24, 21 or 25 that are demonstrated uh, in the demonstration. But there has been paper claiming factorization of large numbers like 291311 using only 3 qubits. So right now, even if you go and check out the IBM's website for quantum computation, they're providing you, I think, 16 qubits to write your own qubit circuit and try to get a gist of how quantum computers are working. And still, if you consider these little amount of qubits, people are making efficient algorithms to break down encryptions. And the numbers being used right now for modern encryption are actually really, really large. And it will take at least 1,000 of qubits to break them. So at the moment, we are kind of safe, but still the future is bringing endless possibilities to break down this uh, problem of integer factorization. And Shor's algorithm is actually promising a very efficient time complexity of log n to factor integers. And yes, that was all for this presentation. Now I'll demonstrate to you a little um, how Shor's algorithm is producing these factors. So I use this library called Qiskit, which is being provided to get a gist of how quantum computation would be. And it has implemented a lot of algorithms, including Shor. So here if I've input 15, which is a really small number, and send it to send it for factorization. So you can see that for n, let me just increase. Yeah, for n equals 15, it's providing the factors 3 and 5. For 25, it's providing the factor 5. And if I take 21, it's providing me factors 7 and 3. And actually, on my system, it is also taking a lot of time to produce these small results. So you can see kind of how
So did you
laggy
use
the
some?
classical.
So Ashish,
Yes,
did
sir.
you use some real quantum computer? I mean, did you submit it to certain qubits for the factorization or in the Qiskit or no?
Actually, sir, I wanted to use that. That is being provided by IBM. IBM is actually providing 16 qubits for us to play with them, but getting to know how that qubit circuit is found was very difficult for me, and I couldn't implement it there. Else, I would have
Okay.
shown you there, but it
So
was
do
really
you
difficult to. Yes, sir.
so do you understand what is alpha times cat 0 plus beta times cat 1?
So the Schrodinger's equation you're talking about?
No, no, the basic qubit. So single qubit is basically a linear combination of two vectors. So basically single
Yes,
qubit
yes,
is
sir.
a,
Factors.
it's just a two-dimensional vector space, Hilbert space
Yes,
actually.
sir. Yes, sir.
Okay. And two qubit system is a four-dimensional Hilbert space, and so on.
Yes, sir.
N qubit system is 2 raised power n dimensional Hilbert space. Yeah,
Yes,
I
sir. Yes,
think,
sir.
but I think you have done a good job because did you had any initial background in this area or was the fresh you started?
No, so it was a very fresh start, and it was actually really interesting for me to get into quantum, to know about this quantum realm. So yeah, my curiosity got me into thinking of stuff about this.
Good, good. Yeah, so there are some many interesting books and the things you can look at it. Qiskit has also a textbook which where you can implement the circuits actually easily. An online textbook,
Oh,
free provided by IBM actually. And
yeah, I
through that,
read that book, but yeah, yes, sir.
yeah, yeah. So I mean, yeah, that if you look at it, you can quickly learn it. Yeah.
Yes, I tried, but yeah, there were no other documentation and other help available on internet, so I was not able to do it quickly. But yeah, I got the gist of how these qubits are working and what the nature of these mechanics could be and how much possibilities are there. Just within the first computation, it is giving us a superposition of all the result sets, and that was really interesting to know.
Okay, okay. ठीक है, ठीक है. Thank you. So I think
Yeah, thank you, sir.
please send me all your these things, presentations so that I can finally look at the give you the marks and so on, right? Okay.
Yes, sir.
Okay. Thank you. Thank you.
Okay, thank you, sir.